This is Algebra 2, Chapter 0, Section 4, in which we look at counting techniques. Now, I'm not talking about something as simple as 1, 2, 3, 4, 5. Although you could do that, it might take a while for some of these problems. What we're looking at is possibilities. We're looking for something called a sample space, which is nothing more than everything that could happen in an experiment. If it's something simple like flipping a coin, the sample space is heads or tails. Rolling a die, the sample space is 1 or 2 or 3 or 4 or 5 or 6. Okay. Now we could use a tree diagram to show everything that's in a sample space. But if you have a large number of outcomes, this can get to be a pain. So sometimes it's easier to use what's called the fundamental counting principle. And the idea here is you take the number of outcomes for each thing and multiply them together to make the total number of possibilities. So let's consider this. We have a bike manufacturer. They make 5-speed bikes or 10-speed bikes. And their bikes are made in 7 different colors with 4 different frame sizes. The question is, how many different bikes do they make? Well, we could make a tree, and the first split would be 5-speed or 10-speed. And then under the 5-speed, you could break out into the 7 colors. And then under each color, break out into the 4 sizes. And then do the same thing under the 10-speed side and then count them all up. That sounds like an awful lot of work to me. So let's use the fundamental counting principle. There's 2 different speeds times 7 colors times 4 sizes makes a total of 56 possible bikes. 56 different bikes that they make. And now I'll ask you to pause here and give one a try on your own, and then come back and we'll check it out. So our businessman has 6 shirts, 4 ties, 8 pairs of slacks, and 5 pairs of shoes. So this stylish guy here could make 960 different ensembles. 6 shirts times 4 ties times 8 slacks times 5 shoes. Making a tree for that would have been a lot of fun. Now sometimes what we have to deal with are making arrangements of objects in which the order matters. And when the order matters, we call that a permutation. Okay. Running a race, the order that they finish matters. The first one to finish gets so many points, the second one gets this many, and so forth. You know, the order that you finished in makes a difference to what medal you could get. So that would be a permutation. So let's consider having the letters A, B, C, and D. How many ways can we rearrange those letters together? Well, how many letters could we pick to go first? 4 of them. We have an A, a B, a C, or a D. Now that we've picked a letter, how many letters do we have to choose from next? We have 3 letters left. Then how many? 2. And then how many? 1. So we have 4 possibilities first, times 3, times 2, times 1. Gives us 24 possible arrangements. When you have something like that, where it's 4 times 3 times 2 times 1, That's 4 factorial. The symbol for factorial is the exclamation point. We're not getting really excited and saying 4! Okay. The symbol for factorial is this exclamation point. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Whatever factorial it is, it starts at that number and goes all the way down to 1. And a lot of times your calculator will have that button on it. And if you ask me in class, I'll be more than happy to show you where that is. Okay. And in fact, here we have an interesting situation. We have 8 runners in the finals of the 100-meter dash. Question is, how many different orders can they finish in? Well, we can have 8 different people could finish first, 7 could finish second, 6 could finish third. So there's 8 times 7 times 6 all the way down. 8 factorial, which my trusty calculator tells me is 40,320 possibilities. Okay. Now let's look at this situation. We have 20 candidates up for 6 offices in a club. And we're just everybody's gonna vote for 6. Whoever gets the most votes will be the president. Second most votes will be the vice president, and so on down the line. How many different orders are possible? Well, this is going to get really big really fast. So it's nice to have a calculator button to do the job. And your calculator most likely has a button, maybe hidden in a menu. But the button is NPR. The P stands for permutations. N stands for how many things you have, and R is how many you're choosing. So we would have 20 candidates that we're choosing 6 of. So to put this in our calculator, we would put in 20, and then the NPR button, and then 6. And our calculator comes up with this beautiful answer of 27,907,200. And again, I'll be more than happy to show you where those buttons are on your calculator. But it's different for each model, so it's easier just to show you individually. Now we've talked about where order does matter. There's another situation where order doesn't matter. And we call that a combination. Okay. To do combinations, it would be like if I said the first 4 finishers in the race are on the Olympic team. Doesn't matter whether I finish first, second, third, or fourth. If I make the top 4, I'm on the team. That would be a combination. Okay. Similarly, if we're taking cards out of a deck, it doesn't matter when I get the ace of spades. As long as I have it, that works. So how many ways are there to choose 5 cards out of a standard deck of 52? We need a different button, NCR, C for combination. Remember, that means the order doesn't matter. So we would put in 52 NCR 5. And my calculator tells me that's just over 2.5 million, 2,598,960 different ways to get 5 cards out of a deck of 52. And that must be the last slide. So hopefully, as always, if you had questions along the way, you jotted those down. And we will see you in class.